Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 27, 2025, about 2 days ago. The big result is that the proposed system hits 85.6% average success on OmniAction Libero TTS, vastly ahead of the best baseline at 25.9%. The paper is titled RoboOmni, Proactive Robot Manipulation in Omni-modal Context, and as we'll see later, the results are really impressive. In short, this paper unifies speech, environmental audio, and vision to infer intent proactively, introduces the large OmniAction dataset, and delivers faster inference with stronger intention recognition. Also, the authors shared the official repo. It includes training and inference code, scripts for pre-training on OmniAction and fine-tuning on Libero, clear environment setup and data layout guides, plus evaluation commands. You'll find a small model zoo, experiment utilities, and runnable examples to reproduce results and benchmark performance end-to-end. On Hugging Face, you get RoboOmni weights and fine-tuned Libero spatial and goal checkpoints, model cards with inference snippets, training datasets, and example pipelines for proactive vision audio action control. Alright, Figure 1 maps how robots receive instructions and what that means for control. The left panels contrast direct or complex commands with inferential cues and compare text, speech via recognition, and raw speech sources. Cross-modal contextual instruction means the robot infers intent by fusing speech tone, environmental sounds, and vision, then asks for confirmation. The right panel illustrates this flow, showing dialogue understanding, visual grounding in the fridge scene, and final action execution with a brief spoken check. So, Figure 3 shows how OmniAction spreads examples across contextual instruction types. The bulk falls under dialogue-style signals, with dyadic two-person and single-speaker variants making up the largest share. The chart also includes nonverbal cues and overlapping speech, which mean environmental sounds or simultaneous talk that the robot must parse to detect intent. Smaller but important slices cover identity hints, sentiment tones, and triadic dialogue, which involves 3 participants and indirect references, so the dataset pressures the model to track who means what. So, Figure 2 shows how OmniAction is synthesized, turning plain commands into contextual dialogues, rendering audio, and packaging examples for training. The top band outlines textual scripting, which filters scenes, rewrites commands into multi-turn dialogue, extends interactions, and runs a validator. The middle band depicts auditory realization, with speech synthesis, multi-speaker simulation, environmental backgrounds, and non-verbal event insertion, followed by human verification. On the right, the examples panel illustrates 6 intent types, including sentiment, overlapping talk, and identity cues. Well, Figure 4 presents the whole control pipeline, showing how perception, reasoning, talking, and execution connect to act on intent. A shared token space means audio, vision, and text become compatible units so one model can reason across them. The perceiver embeds signals, the thinker decides, the talker replies in speech, and the executor outputs 7 degrees of freedom actions. The left panel highlights OmniAction scale, while the right panel illustrates a dialogue where the robot confirms intent before moving. Alright, Table 1 reports head-to-head results across tasks and contextual instruction types, which means intent cues come from tone, identity, overlaps, or multi-speaker dialogue. RoboOmni leads with an average success of 85.6%. The best text and speech via recognition baselines peak at about 26%. Gains hold across spatial, goal, object, and long horizon suites. The rightmost column shows consistently higher scores, because the model fuses raw audio with vision and outputs actions directly. So, Table 2 compares real human audio performance on OmniAction Libero Real. The bottom row highlights the direct audio input result. RoboOmni leads with an average of 76.6. The strongest cascaded pipeline, Pi0, reaches 73.8. Audio to automatic speech recognition to text pipelines, which convert speech to text before reasoning, lag, with OpenVLA at 40.1. Nora records 17.4. And direct audio helps because it avoids recognition errors from accents and noise. Wrapping up, 2 takeaways stand out. End-to-end fusion of raw audio, vision, and text lets the robot infer and confirm intent proactively, far surpassing cascaded speech recognition pipelines, and the OmniAction corpus unlocks rapid, stable training. The broader implication is smoother, faster human-robot collaboration in noisy, real settings. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.